So this last section on cancer, we'll talk about treatments. Although I do want to mention that prevention is a big thing. People who work on cancer get very frustrated with, they go, we can tell you a lot of ways that you can avoid cancer. Stop smoking, don't be quite as heavy, avoid exposure to certain types of ultraviolet, don't go out and get a tan. There are chemicals to avoid, there's workplace exposures to avoid, and they know that information's all out there, and we're people, and we know stuff is bad for us, and we do it anyway. But it's for people that are working in treatment of a disease where they look at the victims and go, they might have avoided this. You can see how it gets them frustrated. When you're usually going after a disease, you want to be able to target and counteract something that is happening. When it's an invader, bacteria, viruses a little bit, parasites, there's usually some aspect of chemistry going on in the invader that you can go after that our own cells don't do. That is much trickier with cancer since it is our own cells. And a tremendous amount of what we're going to try to poison is going to poison cells that are doing the same thing for a normal existence. So if you're going after a lot of stuff having to do with division, then it's going to affect dividing cells. So you're going to get, your hair's going to fall out, you're going to get skin rashes, you're going to get stuff along the linings of your two major internal systems with linings, your respiratory system and your digestive system. And it just kind of goes with the territory. If going after dividing cells, you're going to go after dividing cells. I mentioned anti-angiogenesis. That looked like a good target because in adults we're not doing that. But a cancer tumor, in order to get blood vessels to invade, may be releasing chemicals that we could counteract. Turns out not to work as well as everybody had hoped. The ways that cancer cells evade the immune system are things that your own cells typically don't do. So trying to kind of wake your immune system back up to take that camouflage away is another potential approach. Going specifically after glycolysis. Your cells do glycolysis, but they also feed in molecules from protein breakdown and from fatty acid breakdown. And so glycolysis isn't necessarily, if you can counteract it, not necessarily going to do a horrible amount of damage to other cells. When it cells in hormonal systems, in glands, that was the word I was looking for, then the cells may have interactions with hormones that you can counteract. We talked about that with breast cancer, where breast cancer cells are cells that are interacting with estrogen. And if you can block estrogen or block its ability to connect to the cells, then you may be able to kind of set them down so that they don't turn cancerous. Something I read recently is that one of the enzymes that cancers tend to activate, I don't have down what it does, but it's something that's good for the cancers, but not that big a deal for us. It has a copper-containing prosthetic group in it, and so there's some attempt to restrict copper in the diets of people that have cancer to maybe block the ability to build that particular protein. And there's a bunch of work. This is fairly new, so I've just read about it, and it isn't that specific. But the idea of, can we come up with toxins that are very, very targeted at something specific that's going on in cancer cells that really isn't happening in other cells? That's kind of a growth area, at least at the moment. Problem is, as we learn how things work, if you're designing pharmaceuticals, you go, oh, okay, we can go after that. And then it turns out for one reason or another, which we'll talk about in the last chapter, you can't necessarily go after it, or you do go after it and it doesn't seem to work. There's a reason why, the vast majority of pharmaceuticals never make it to the market, because for one reason or another, they just are not, they don't work. Radiation. If the cancer is localized, you can hit it with radiation, but you have to hit it with a lot of radiation, which is why you can't dose a whole body in the level of radiation it takes to, remember, it breaks DNA, fragments chromosomes, and then the cells divide and then need something that they don't have, or they use something that they got too much of, and so it can be very effective at killing dividing cells, usually post-division. But in order to hit a tumor, and this is something that you use on tumors, and not really mess up, okay, the tumor's here, you've got tissue above it, you've got tissue below it, the X-ray beam is going to go right on through. In order not to mess up the tissues around it, you hit it simultaneously with multiple beams, where this beam coming through isn't doing that too much to this tissue, but it's hitting the tumor. Same thing's true here. Same thing's true here, and the overlap point is the tumor. The tumor's getting a hefty dose of radiation, but it's multi-beam radiation coming in from different angles, so that the overlap is pretty much there. Chemotherapies, chemicals. Oh, don't go on chemotherapy, it's poison. Yeah, it is, it's supposed to be. It's going after things the cancer cells are doing. It's gonna have effects on other cells in your body. It could even produce cancer in other cells that are not cancerous yet. But it's one of those trade-offs that people have to kind of put up with in order, if somebody offers you a cancer treatment and that has no side effects, the reason for that is it has no effects. It's not gonna do anything except possibly make you feel better for the placebo effect, which is not nothing, but it isn't gonna make your cancer go away. Targets of chemotherapy, replication, obviously. The ability to make the right kind of nucleotides that are necessary. Spindle formation, right? That's gonna affect division. We talked about telomerase and how cancer cells that turn on telomerase are much more successful replicating. And the issue is that you start to sort through cancer cells that respond to the poison, and you start to select cells that are not so responsive. Resistance crops up in your population of cancer cells. Right now, the biggest growth area in cancer treatments is in immunotherapy. A couple of months ago, article that I read about it suggested that there were over 3,000 clinical trials of various types of immunotherapy going on in the country. A lot of people with cancer. What they're working towards is treatments that are very individualistic, where they're going to do a lot of genetic testing and a lot of testing of your immune responses in order to pick and choose what will or won't work on you. That's going to be possibly very useful, but incredibly expensive. That is part of the American medical system. One of the reasons that things are really expensive is that we do really expensive things. That's not the only reason. There's also a lot of profiting that probably shouldn't be happening, but we get some of the best treatments in the world, and those are not cheap. Okay, looking at some of the approaches for immunotherapy. There's what they call checkpoint inhibitors that cancer cells will produce so that immune cells can't connect to them and interact with the cells. And so there's chemotherapies that try to block the blockers, basically. When your immune system is trying to fight cancers, there's a phase that the system goes through that's called T cell. T cells are your primary fighters. And you get something called T cell exhaustion, where they just get less and less effective at doing what they're supposed to do. And so that's something that's very much being studied. Taking and selecting out immune cells that are specifically targeted at your particular tumor, and then cloning them, making a whole bunch of copies and then putting them back in, what they call adoptive cell transfer. One of the issues that is a possibility for immunotherapy is that as you boost the immune system, you may see autoimmune side effects. One of the early immunotherapy results that I saw last year suggested that type 1 diabetes was not a hugely common side effect, but it was a side effect they noted in their study group, and it wasn't a huge study group at the time. Vaccines. If your cancers express particular antigens, there may be a possibility of giving you different types of activity level vaccines, so that if that cancer recurs, you'll actually fight it, is that you'll already have the immune system ready to go to fight it. And then I talked about the microbiome. They're still trying to figure out how to involve the microbiome. Used to be that the assumption was, so we treat you. Your tumors shrink. You go into remission. Remission, essentially, it's the cancer stops progressing, but hopefully remission involves reversing it. And what's called total remission is we can't find the cancer anymore. And people go, does that mean I'm cured? And the answer is, we can't find it, but we don't know, that doesn't mean it's not there. Is that if we've reduced your cancer population so that you have little pockets of cells someplace in your body, then we won't know, those won't show up on any of the scans. So if they're in place and they continue to grow, the benchmark that they came up with a while ago was, because people want to know if they're cured. So one of these big meetings of oncologists, they went, so say we reduce the population of cancer cells to just one cancer cell of this original cancer. When are we going to know? When's it going to come back to a level where it's going to show up again? And they decided that 3 years, almost any cancer that people were familiar with would come back within 3 years to a visible level. And they kind of got conservative and said 5 years. So 5 years of total remission, we're going to call that cured. They're starting to back off of that because it turns out that you can produce what are called cancer stem cells, that you get cancer cells that go dormant on you. And because the assumption was if we reduce to one cell, that cell is an active cancer cell. And if it continues to be active at a certain point, we'll know it's there again. But if the cells go dormant, we're not sure how long they can stay dormant for. And it's tricky. Say 10 years have gone by, you had breast cancer, you have breast cancer again. Is it the same cancer? Well, look at the genetics. But it's the same sort of cancer in the same person. So you may get similarities in genetics that don't really connect to the original cancer, just connect to how the cancer develops in this particular person. So that's a question that has not been answered, and I'm not sure how easy it's going to be answered. Okay, so we pulled a lot of stuff into this particular chapter, so I hope it all made sense to you. That's why I'm basically lecturing, because I'm trying to hit the stuff that's in your head to go, oh, mitosis, spindle formation, chromosome damage, mutation, all that stuff, all things that we've talked about. And so that is it.